Good evening, Prof, and good evening to everyone. Today's program is based on skill acquisition, and the topic is basically on the design and development of a smart irrigation system, which will be delivered by uh, Associate Professor Dr. Elijah, who is an Associate Professor of Computing at Mount Kanu. Dr. Elijah Olakunle is a dedicated researcher, engineer, and academic with expertise in Internet of Things, machine learning, embedded systems, and wireless communication. He holds a PhD in wireless communication from University Technology Malaysia, Johor Bahru, Malaysia, and a master's degree in microelectronics and computing from Beaumont University, United Kingdom. He currently serves as an assistant professor at the School of Computing, Mariam Abacha American University of Nigeria, and is the founder and CEO of Olac Large Engineering Services. His research focuses on AI-driven agricultural innovations, smart cities, and Industry 401 technologies. Dr. Elijah has an extensive publications record with over 3,400 citations on Google Scholar and has actively contributed to multiple national and international research grants. He is also a recipient of several prestigious awards recognizing his excellence in research and innovation. He is passionate about technology and digital skills development. He mentors students and professionals in embedded systems, data science, IoT, and artificial intelligence, fostering the next generation of innovators and engineers. Kindly, we kindly help to welcome Dr. Olakunle Elijah to start his talk. You are welcome, Dr. Elijah.
All right. Thank you very much, Engineer Yaya, for that introduction. And I'd like to say good evening to everyone, whether good evening or morning or afternoon, wherever you are watching from. Before I start my presentation, I would like to say a big thank you to Professor Adamu Abubakar Gwazo, the President, Mount Group of Universities, and also Professor Dr. Muhammad Isra, who is the President of Miriam Abacha American University of Nigeria, Kano. I'd like to say a big thank you for giving me this platform to share my little knowledge with some of our aspiring students and also our invited guests who are from outside of my own family. So without waste of time, I'd like to quickly go through what I'll be sharing on today. So basically, this seminar, this talk is on design and development of smart irrigation systems. And the outline for today's talk is first, I would like to talk about the aim of this training, then introduction to irrigation systems. Basically, I'll be spending more time on how to design and develop smart irrigation systems. And then I'll open up for questions and answers. So let's start with the aim of this training. I came across this statement that was made by Mr. Strive Masiwa. Is a very popular African billionaire, one of the wealthiest men in Africa. And he made this statement. He said, 10 years from now, the wealthiest Africans will be young people sitting in their bedrooms building AI apps for agriculture, health, and food security. All right. So based on this statement, one of the aim of this online training, which we have started and it's going to be in form of series, is to inspire our young minds to become, to be among the wealthiest Africans by developing innovative solutions that will solve real life problems. Okay. So we started this in combination with some of our colleagues, Associate Prof. Jubre Musa Mwazu and Engineer Yaya, where every Friday during the school session, we meet with the students, we provide them physical training on Python, on embedded systems, and so on and so forth. And we are building on that by opening their eyes and inspiring them to see how they can begin to use those skills to solve real life problems. And that is why we've chosen to start with this one tonight, which is designing and developing a smart irrigation system. All right, so before we go further, I'd like to introduce us to what irrigation system is all about, okay? So an irrigation system is a method or setup used to supply water to plants or crops artificially, all right? So any system that is designed to supply water to crops or plants artificially is known as an irrigation system. And we have different types of irrigation system. We have the surface irrigation system, we have the sprinklers, we have the drip irrigation system, we have the subsurface irrigation system, we have the center pivot irrigation system, and we have the manual irrigation system. If we look at around us, we'll notice that most of the irrigation system or the common type of irrigation system we have is still the manual irrigation system. Manual in the sense that it's either you are connecting your pipe to your tank to water your garden or to water your crops, or you are actually fetching water with some container to go and water your crops or your garden. So this is still very common, and of recent we're beginning to see some sort of drip irrigations, people who are setting up their greenhouse. We are beginning to see sprinklers for large-scale irrigation systems, and also the center pivot. Some of these have been introduced by government now on a large-scale farming, where they set up some vehicles to sprinkle the farm. All right. So these are different types of irrigation systems. Now, we're talking about smart irrigation system, all right? So a smart irrigation system is an automated watering system that uses sensors, data, and technology, all right? Like the Internet of Things, IoT, to monitor soil conditions, weather, crop needs, and then automatically adjust water supply only when and where it is needed. So talking about sensors, so we have sensors that are inserted into the soil. We have sensors that are there to monitor weather data parameters, all right? So these sensors gather information from the physical environment and they send it to the microcontroller device. So the microcontroller device also is an IoT device that transmits this data to maybe a cloud server or application server where the data are analyzed, processed, and based on that is able to control the supply of water either to the garden or to the crop or to wherever we want to apply it. And apart from that, we can access this data or control of this irrigation system using our mobile phones or from a dashboard. Now, there are several use cases of smart irrigation systems, okay? So it could be for greenhouse. So greenhouse, maybe you want to do a set up a greenhouse that protects your crops. You want to protect your crops, then you can set up your greenhouse. It could be for urban parks and landscaping. For example, in Mahun now we have very beautiful landscaping. Okay, so we can decide to automate it so that it sprinkles water at the right time and the right quantity and all of that. So that makes it a smart irrigation system. All right. Then it could be for home gardens or lawns. You could set up your smart irrigation system for your research and demo farms. So research that are focusing on different crops, they can set up their own smart irrigation system. Then data-driven farm management, all right? So this is where you're talking about predictive watering, when you want to predict the amount of water that you need to supply in order to avoid some diseases that are affected to too much water, all right? So data-driven farm management. Then water scarce regions. This talks about the northern part of Nigeria where during the dry season, it could be very dry, then you need some water supply, all right? So maybe you make your borehole and things like that. All right, so now let's look at the design and development of smart irrigation system. So this is a very basic setup, which I'm going to talk about now. So in most cases, you need a water reservoir. So your water reservoir could be an overhead tank, right? That stores water that you need to supply to your plant or to your farm or to your gardens and so on and so forth. So basically what happens is this, you in most cases, you have your maybe borehole or underground water where you take your water from. Some source of water could be water harvested from the rain. During the rain season, you harvest the water and you store it up in your reservoir, all right? So this is a submersible pump that shows this is taking water from underground, all right? And is supplying into the tank. Now, from this water reservoir, we need to supply water to our farms, to our crops, to our gardens, our lawns, and so on and so forth. So that is where we need a smart irrigation system. So this is a simple setup where you have your controller, okay, that controls when to supply water to your garden, all right? Then you have your sensor that monitors the soil condition of your garden or your farm or whatever you are supplying water to, right? So this sensor monitors the condition, sends the information to your microcontroller, your controller decides to activate your valve. So we have an electronic valve that supplies, that allows water to be supplied from the reservoir tank to the sprinkler. So this is an example of a sprinkler. Or if you decide to use the drip irrigation system, the valve supplies water to your drip irrigation system and it waters your farm or your crop or your land. So this is a basic setup. Now, I'm going to spend more of the time on how this controller is designed in order to make our irrigation system smart. So first, we need to get the design requirement, all right? So in this case, this is just a simple scenario where we are monitoring the soil condition, okay? So for every condition you will be monitoring, you will need to specify the threshold. So let's say we are monitoring the soil condition. So maybe the soil moisture, percentage of moisture should be, once it's less than 20%, it should trigger an alarm. Okay, the purpose is to warn that plant is at risk. Okay, then we could measure the temperature. Okay, when it is dangerously high, so we use a sensor to measure the atmospheric temperature. So in some cases, when the temperature is too hot, it could trigger what they call these bushfires and all of that. So we need to we can create an alarm system that triggers. We could check the normal soil dryness. Okay, so maybe in a normal condition, once the soil moisture is less than a certain percentage, it wouldn't trigger an alarm. However, it will trigger irrigation only. It will switch on the water valve to supply water to the plant or to the lawn. All right. Then we could check high temperature plus low humidity. Okay, maybe if the temperature is above certain degrees and the humidity is less than certain degrees, it's not a critical situation. Don't trigger the alarm. However, trigger the irrigation system, that is, switch it on to supply water. Then we have a situation whereby we can also monitor the irrigation on and off. That is, in this case, we check when there's a pump state change. So anytime there's a change within our pump supply or the valve supply, it just gives us a short single beep. All right. So the controller will give us a short single beep. So this just provides some sort of notification. All right. Then when the irrigation system is on, that is the pump state is on, it could provide some short periodic beeps. Okay, so again, this just provides some notification that some activity is going on the smart irrigation system. So this could be an example of the requirements on how you want your controller to behave, right? So next, we're going to look at how the controller can be designed. Now, on this diagram, we have various electronic components, okay? So we have the microcontroller, which is called the Raspberry Pi Pico W. It's a very powerful microcontroller that was developed for IoT application, prototyping, and so many useful applications, right? So this microcontroller, we have an OLED, organic light emitting diode. So this displays the information we want to see on the controller, all right? Then we have a buzzer that sounds the alarm each time an activity takes place, okay? Then we have our relay that controls the valve, all right? So this is the relay as an electromechanical device that switches on the valve for us and switches off the valve. Then we have the what they call the capacitive soil sensor. In this case, I will talk about each of these components as I move on. Then we have the DHT22. So the DHT22 is to measure the temperature and the humidity of the environment. Okay? Now, before we continue with the design, we need to do what they call pin mapping. So pin mapping tells us which of the pins on the microcontroller is connected to which electronic component, okay? So in this case, we have the OLED, which is this OLED. The SDA is connected to what they call the GP0. That's the first pin here. And the SCL, which is this one, is connected to the GP1, okay? So the microcontroller has a pin configuration that we need to understand how to read and how to use. Then the capacitive sensor is connected to GP27, which is analog to digital converter. All right, so this one, analog to digital converter. Then the relay, this is the relay, is connected to GP13 at this point, okay? Then we have the buzzer, which is connected to GP18, and we have the DHT22 output pin, which is connected to GP2. So for the purpose of those who who have little knowledge about electronics, I want to talk about each of these very quickly. Now, so let's start with the soil moisture sensor, all right? So we have various types of soil moisture sensor, but in two categories. One is the capacitive soil moisture sensor, and the second one is the resistive soil moisture sensor. So for some of us who are into project designs, DIYs, we probably must have come across some of these sensors. Now, when you're dealing with a smart irrigation system, what type of sensor is most appropriate? The capacitive soil sensor is the best or the recommended for your soil smart irrigation system. Why? Because number one, it's suitable for wider range of types of soils. So for different types of soils, it's more suitable. It lasts longer, it's more accurate, more durable compared to the resistive soil moisture sensor. If you use this, after some time, it will start corroding, all right? So it's going to lose its property. In terms of durability, no. Accuracy, it begins to misbehave and not very stable. So I recommend that you get a capacitive soil moisture sensor if you want to develop one. So next is the OLED. So the OLED display has two main lines, which is the serial clock line and the SDA, that's serial data line. All right, so it uses the I2C, that is inter-integrated circuit protocol. All right, so the good advantage of this I2C protocol being used by the OLED is the fact that from your microcontroller, you can just use two wires to communicate with as many I2C devices. So I can have the OLED connected to just these two wires. I can have another sensor, for example, BME 280. I can have another microcontroller using I2C. So with just two wires, you can communicate with so many devices. So that's why it's very good for embedded systems designs. Next is the DHT22. So the DHT22 sensor measures the temperature and humidity. And again, this is the specification, all right? So for humidity, it measures from 0 to 100% humidity. And for temperature, it measures from -40 to about 80 degrees centigrade, okay? So it's quite stable. And some of these properties you need to consider when you are developing your firmware for the design. So it measures, it can only measure the temperature and humidity every 2 seconds. All right, the next is relay. So relay, again, is an electromechanical switch, all right? So you send in your trigger from your microcontroller into your in pin, and with that, you can switch on and switch off. So your valve your electronic valve is connected to the common and the normally closed or normally open. So this controls your valve once you send a signal from the microcontroller into the in pin of the relay. Now, this is the Raspberry Pi Pico W microcontroller. Again, it's a very powerful microcontroller. It does several peripherals, input peripherals. You can use it for IoT. You can use it to do so many things. The processor, it uses dual core processor, quite powerful, and it's very reliable. And it has various versions. Even if your system is going to be more complex, you can use either the Pico 2 W if you are dealing with more complex systems. All right, so here again, so this is the complete circuit and this is how it works. So next, I'll be going to how to develop the codes that will control our smart irrigation systems. So when you talk about developing the codes that you program into your microcontroller to control all of this smart irrigation system, what you are doing is you are developing a firmware. So the firmware is the code that you write to control your irrigation system or whatever embedded system you want to control. Now, to do this, you need a software called the Tony IDE. All right. So we have introduced some of these to our students. They are familiar with the Tony IDE now. You can download the Tony IDE by going to this link. You either download for your, if you're using Windows or Linux or Mac, you download whatever version you want to, you are currently using. Then you need to program your microcontroller, okay, your microcontroller with another firmware called the MicroPython. So it's more like the OS operating system for the microcontroller. So we have MicroPython, we have CircuitPython. And to download the MicroPython and install into your microcontroller, you need to go to this link, okay? Once you go to this link, it will show you this Pico. You have to select. So if you're using the Pico W, you click on the Pico W and it will download what they call the UF2 file for you to install into your microcontroller. Okay, so now once you've done that, the next thing is how you want to develop your firmware. First, there are about 5 steps I've been able to outline. So the first step is what? Import the necessary libraries. So if you are using any components, some components require special libraries. So you need to import all your libraries into your Tony IDE. Then after that, you configure your GPIO pins. Then you define or initialize parameters. So like all those thresholds we have for temperature, humidity, soil moisture sensor, and whatever. So you define all your parameters. Then you need to create functions. So either one function could be to read the temperature and humidity from your DHT22 sensor. Another function could be to display the information on the OLED. And so you create several functions that are needed for the smart irrigation system. Then the 5th one is the main code. So this is the code that runs continuously as long as the system is powered on. So I'm going to show you how to develop this firmware. Now, thank God for AI. So with the help of AI, these things can easily be done. So you don't have to worry too much about developing the codes. What you need to worry now is how your electronic system should operate. Okay, once you know how to use the electronic components, how to connect, how to build, then writing the firmware has become very, very easy with the help of AI. So to do that, what you simply need to do is what? Go to your ChatGPT, all right? So you need to provide your ChatGPT the necessary information it needs in order to develop the firmware for your smart irrigation system. So let's look at this prompt I've written here, okay? It says, provide a complete and well-documented MicroPython code for a smart irrigation system using the Raspberry Pi Pico W. The system should integrate a passive buzzer, all right, a DHT22 temperature humidity sensor, capacitive soil moisture sensor, 5-volt relay module, and an OLED display, SSD1306. Use the following pin mappings, all right? Remember, I talked about the pin mappings, okay? The OLED SDA should be connected to GP0. SCL GP1, capacitive soil moisture sensor GP27, relay in, that is the water to control the water pump, GP13. Passive buzzer should be connected to GP18. DHT22 sensor to be connected to GP2. The code should continuously read soil moisture, temperature, and humidity, display all readings on the OLED screen, control irrigation using both soil moisture and DHT22 readings, such that irrigation turns on when soil moisture is low or when temperature is high and humidity is low. Irrigation turns off when moisture is adequate and environmental conditions stabilize. Activate the passive buzzer if moisture is critically low or temperature is dangerously high. Use clear comments, modular structure, proper variable names, and thresholds that can be easily adjusted. So this is the prompt I'm going to give to ChatGPT, and it's going to develop the firmware. So I'm going to demonstrate that quickly to us now. So let's open my ChatGPT. So this is something I've done, but I just want to show you how ChatGPT will handle such a prompt for our smart irrigation system. Okay, so just 1 second. Let me copy the codes, the prompts. Okay. Control C. Okay, so I believe you can all see my ChatGPT now. So this is my ChatGPT open, all right? So I will just copy and paste that prompt I read now. So just this off. So this is the prompt, okay? So I will just send to ChatGPT and let's see how it's going to generate our firmware for us. Okay. All right, so so you can see ChatGPT is currently coming up with the solution, all right? So it says, nice, here's a complete ready-to-run MicroPython program for the Raspberry Pi PicoW that implements the smart irrigation system you described, all right? So it reads a capacitive soil sensor on GP27, that is ADC1, reads DHT22 on GP2 and all of that, okay? So it explains every step it has taken to come up with the firmware, all right? So this is the code. So the MicroPython code, all right. So first and foremost, you can see it imports the necessary libraries, like I mentioned earlier. So it's going to import all the necessary. So these are the necessary libraries that are needed based on the components we are connecting to our microcontroller. Then these are the configurations, okay, defining the parameters and all of that. The GPIO pins. So it's going to define all those at this point, okay. So the SDA pin is connected to GP01 and all of that, okay. Then after that, our thresholds. So it's going to initialize our parameters, which it has done here. Then the next thing is the functions, okay? So these are how the functions are created. So it's creating various functions for us, right? So this function is the read soil moisture. This function is to read the THT, all right? So again, thank God for ChatGPT for AI, but however, you still need a fundamental knowledge of Python programming, okay? So that was why the first thing we did to some of our students was to provide some basic training on Python programming, okay? It seems there is a bot disturbing our presentation tonight. Somebody, Sadiq, please, if you are the one doing that, please stop. So we have different functions to control the relay of pump is on. So it creates all the functions. So the advantage of creating your firmware in this way is that you are making your firmware designing your firmware in a modular way. Modular way in the sense that you are breaking down your codes into various sections. So it's easy for you to read, it's easy for you to troubleshoot, and it's easy for you to debug. Okay. Then all of these, all right. Then the next thing is the main loop. Okay, so this is the main code section. All right. So where once you power up your code, then it begins to carry out all this operation, right? So once I'm done with this, all I need to do is what? Copy, just click on copy the code. Then you open your Tony IDE, which I'm going to show us in a minute. Okay, so this is my Tony IDE. All right. So once you install your Tony IDE, it's very simple software to use. All right. So then you connect your microcontroller, that is your design circuit. So maybe I'll just hold on here a bit. Let me go back to my slide. Okay. So I'll come back to this section later on. Okay. So this is the code section, right? So we have generated our codes using the ChatGPT. All right. So I'm going to share this slide. So I'll share some of my own codes that I did using the same procedure, okay, for in case you want to make reference to it. So, but before we connect, yeah, so you need to create the prototype of the system first. So there are several stages when you are developing your smart irrigation system. So the first part is the design, which we have talked about. Now is the you need to develop the prototype. Okay, so for the prototype, here is a prototype that can help you to quickly test your firmware if it's working, test all your sensors and your actuators, check your programs that is working before we now go to the next stage of building it up into a standalone system. So to do that, we have what they call the Maker Pipico development kit. Okay, some of our students already have some of these kits which they can use. So with the help of this Maker Pipico development kit, you can set up your system under 20, 25, 30 minutes. You are finished developing your smart irrigation system thanks to technology. All right. If you want to do this years back, you probably may spend several days, if not weeks, trying to do this. All right. So with this Maker Pipico, you just insert your Raspberry Pi Pico W into the onto the board. Then you connect your capacitive moisture sensor, all right, to one of the groove connectors that has the required pin, that is GP27. Okay, so the Maker Pipico is well labeled, well documented, so you can see which pin is going to which component. All right, then your OLED, this is the OLED. Okay, so it's going to GP0, GP1, and it's powered by 3-volt, 3 and the ground. Okay, then the relay. Okay, so the relay is connected to the 5 volts of the microcontroller, and the digital in to GP, I think 2, no, GP13 or GP13, yeah. Then the DHT11 is connected to GP2, okay, of the microcontroller. So with this, you can easily set up your irrigation system under 5 to 10 minutes, and you can begin to test. All right. So now I have this in front of me. Sorry, I can't show you because the camera, but I'm going to connect it to my Tony IDE now, and I'm going to show you how to set that up. Okay, so let's go back to the Tony IDE. All right, so this is the Tony IDE. All right, so the next thing is I need to make sure that my Tony IDE is able to communicate with my Raspberry Pi Pico W. Okay, so with this, okay, so now it's able to communicate. As you can see, there's a prompt there. Then let's say I want to copy the codes from my ChatGPT. So I'm doing this as a real life demo. All right. So I go back to my ChatGPT, I'll copy the code. So I already have the ones I've done, but let's do the ones that the ChatGPT has just generated. So you have a feel of how these things can be done within a very short time, and your smart irrigation system is up and running. All right. So I'm just going to copy it and paste it here, Control V. All right. So when I copy that, okay, then I will just program the microcontroller by clicking the green button. Okay. All right. So you can see it says smart irrigation system starting. All right. Okay. Okay. So right now it's showing me the values on my OLED. So I can ask it to print some of the values on the shell so that you guys too can see what the values are. All right. So I will just go back to my chat GPT and ask it to modify the code so that it can display on the shell. So let's do that quickly. I can say modify the code so that the information is displayed on the Tony IDE shell. Output is also displayed on the Tony IDE shell. So let's see what the ChatGPT is going to do for us quickly. So it says, nice, done. I updated your MicroPython program. So every reading, decision, and pump buzzer action is also printed on the Tony or any serial console in addition to the OLED display. I also cleaned up a small ambiguity that is pump on. Okay, so that's good. So let's see if it's all done. Then I just copy and put into the Tony IDE quickly. Okay, I think it's all done. All right. Okay, so I can just copy this quickly and go to my Tony IDE. It's my Tony IDE. Okay. All right. So I'm going to create a new file so that I have like multiple versions of it. Okay. Again, I'll just click stop first. Then I'm going to run it again and see. All right. Okay. So you can see it's showing me the values on from my soil read. Okay. The raw value is this. The percentage is 71%. Okay. So everything that is showing here is also being displayed on my OLED. All right. Okay, so this just shows you how you could quickly develop your firmware. All right, so it doesn't stop here. Then you could do other things like, for example, you can ask the firmware. So you can check after you've done this, check, you need to test, put your sensors in water. So that takes you to issue of calibration. So calibrating based on the kind of soil you'll be dealing with, okay? Calibration based on the temperature and humidity. So it depends on the kind of crop you'll be working on. If you're just working on your garden, so okay, maybe your garden, so you need to know what is the acceptable temperature before you set up your sprinkler or your irrigation system. What's the acceptable humidity? So that's where a little bit of research comes in. So you begin to play around with those things and you begin to fine tune your thresholds. So once that is done, you test it and it's okay. Then you can take it from your prototyping stage and you can couple it up and build up your smart irrigation system for deployment. Okay. So while that is going on, so let's go back to the slide. Okay, so this again helps us to easily do our prototypes and helps us check our system that is working. And this is particularly good for those who are going to be thinking of projects they want to do for their final year projects. Okay, you can decide to say, okay, I want to do something smart that controls all the watering of the university environment and the lawns and all of that, the landscaping and all of that. Or if you have some farms that you feel they need these systems, then you can begin to look at developing something similar that you can deploy for these farms. Okay. So now let's go to the next, which is, let's see. Okay. So having talked about up to this stage, so there are other things that can be done. Okay, so after you've done your prototyping, then you move on to calibration. So calibration is where I talked about you taking it to the actual site to go and deploy it. So you begin to take readings, values. You check what value. So once you put your soil sensor into the water, the values will change. Okay. So if I take my soil sensor later on, I'll put in some water. You see how the values changes. So based on that, you begin to work out your calibration data to know what is the threshold value, what is the acceptable value for your system to work appropriately. Then the next thing is to implement Internet of Things. So I'll be doing that in the next talk, where I will show you how to convert this to Internet of Things, where from wherever you are watching me, you'll be able to control the system. You can switch the valve on and switch the valve off, okay? You can access the data from the sensor. You can access the data from the capacitive soil sensor, the humidity and the temperature sensor, and all of that. Then you can also change the threshold values. Let's say you are moving to a different place, you should be able to change your parameters without you being there. So you can do that through the Internet of Things. All right. So I'm going to show you how to do that. Then in our subsequent series as well, I will show you how to create a mobile app. So these days, everyone wants to control everything from their mobile app. So from your mobile app, you can also make control your irrigation systems, and you can monitor some of these factors. All right. So create a mobile app that performs the following: set parameters, display the soil moisture, display the environmental temperature and humidity, display the pump status. Then in the future, you can also take it a step further by making it not just smart irrigation system, but you can decide to make it an intelligent irrigation system. Intelligent in the sense that it's able to study the conditions and make decisions by itself, not you programming it to change the threshold values at all. No, it's going to study previous data, and using machine learning algorithms is able to predict if there's going to be rainfall tomorrow, so I do not need to switch on the pump and things like that, or forecast when there's going to be critical temperature or critical humidity, and begins to pre-warn the users or the owners. All right. Then after that, now you can now begin to think about deployment and commercialization. So that's another phase where everything is already working. Now, how do you sell it out to people? How do you make people to begin to buy this smart or intelligent irrigation system? So we'll be continuing the talk. So we'll be addressing each of these as we go ahead. All right. So because of our time, let me just so in summary, so I've talked about what irrigation system is, how to design and develop smart irrigation system, then the future training. So in terms of in the next set of training, we'll be looking at how we can implement the IoT aspect and how we can develop our app. All right. So for those of you who are interested in developing your skills on how to use some of the things I've mentioned in this talk, like the Raspberry Pi Pico and the Maker Pi Pico development board, how to communicate with over about 24 or 25 sensors. So you can get this ebook, which I've written, and most of our students already have it now, which we distributed during the training. So it says MicroPython made easy, Raspberry Pi Pico W projects for beginners. So that will tell you how to use the microcontroller step by step, and how to connect different components to your microcontroller and how to build a solid project. Okay, so for the certificate, I believe the link will have been shared in the chat box. So please feel free to fill the certificate, and thanks to Professor Mohamed Ishra for making this platform available, and also the fact that certificates will be given out to everyone who has joined.
Producer.
All right, so in terms of my research profile, so this is my research Google Scholar Undo. Okay, so you can go click on, again, for those of you that register, we'll share these slides so you can have access to some of this information. But you can just Google my name, Olakune Elijah, and you see some of my research work. And if you're interested in any research and collaboration, please feel free to get in touch. So I'll be more than happy to work with you on whatever research you'll be working on, whether agriculture, smart this, smart that, anything else to do with IoT, AI. More than happy to collaborate with you. So on that note, I would like to say thank you for giving me this time, and I'll pass the time back to Engineer Yaya.
Thank you very much, Dr. Elijah, for the wonderful presentation. You all agree with me that Dr. Elijah have actually make a wider uh, presentation and then give us a wider scope on how we can develop our research on agriculture. He talked about briefly. Let me briefly go through what he has said. He defined the irrigation system design of the controller, where he mentioned the different types of microcontrollers, and then where he talked about the pin mapping, the design on the irrigation system, different component that forms the irrigation system, the OLED, the relay, the buzzer, the Pico, and then the DHT. He talked about two types of uh, soil sensor, which are the capacitive soil sensor and the resistive soil sensor. And he talked about why the need for us to use the capacitive soil sensor. He talked about after that, he now dwelled on the software part of the work, where he talked about the Tony IDE, the MicroPython, which is basically the programming language for the systems, and then he talked about the developing of the firmware. He looked at these different types of steps that are involved in it, where he talked about the import. The import necessary libraries, the configuration of the GPIOs, the initialization of the parameters, the creation of your function of functions, and then the main code. He showed us how we can leverage on AI tools such as ChatGPT in creating our code, and then he make us to know that our strength will lie on the electronics part, and then we can leverage on the AI to generate the code, and then provided that we know the pin mapping of all the necessary hardware, then the AI can give us what we need to program the system to get the desired result. Thank you very much, Dr. Elijah, for the uh, for the skill acquisition this evening. The floor is open for anyone that have a question so that he can answer it. Thank you very much.
Thank you, Engineer Yaya.
If you have a question, a contribution uh, for the talk, please, you can raise up your hand, signify by raising up your hand so that we can call on you uh, for your response. Thank you.